Another method to use when dealing with 3D forces is coordinate format. In this case, this problem is asking you to record the answers in coordinate format. Now, there's no right or wrong coordinate versus Cartesian. They're just two different methods. This lecture will illustrate how to use the coordinate format. So before I begin with the working diagram, a couple of notes about the way the forces are recorded. You will see that the 600-pound force here is shown with extension lines drawn to the z and x axes. Once again, this means that it only has a z and x component. The y component is 0. This 400-pound force is drawn going below the xy plane, hence it will have all three components. To begin this problem, we're going to need a working diagram. Our working diagram, as always, should include a sign convention. It should label our forces and should also label our angles. The other angles I need to label are this angle right here, which is between F2 and the negative z-axis. Since from the positive z-axis to the negative z-axis, that would be 180 degrees on the whole line, and this angle here is 120, that means that this angle here, which I'll call gamma, equals 60 degrees. We will also need to label this angle here between F2 and the y-axis. That angle is beta, and we're going to have to find that. You will notice that beta is between F2 and the y-axis, alpha is between F2 and the x-axis, and gamma is between F2 and the z-axis. We can now find beta. In any 3D system where you have three coordinate angles, and coordinate means that all three of them share the same ordinate, we can say that cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. By the way, this notation right here, cosine squared gamma is the same as cosine of gamma squared, quantity squared. It's just a shorthand notation. We need to now solve this equation for beta. The cosine of beta equals the square root of 1 minus cosine squared alpha minus cosine squared gamma. So then you can just take the inverse cosine of both sides. Once again, I'm able to take some shortcuts with my algebra here because I'm working inside an auxiliary computation. And beta equals 45 degrees. Step 2, I would say solving for x, y, and z resultants. So I'm going to start with frx. And frx equals plus or minus f1x plus or minus f2x. frx equals f1x is f1, and it's a positive. It's going in the positive x direction. f1 times, now you'll notice that 4 corresponds with the x-axis and 5 corresponds with f1, so that's 4/5 of f1. Plus f2 is also going in the positive x direction. And in order to figure out f2's x component, well, we have f2 here, and there's an angle measured between f2 and the x-axis. So we could draw a right triangle that would be made up of f2, the x-axis, and then a diagonal line between the two of them. That right triangle has a 60-degree angle there. So that would be cosine alpha times f2. Now we can plug our values in, and frx equals 680 pounds. Once again, remember that that needs to include a positive sign. Underline your answer 3 times, and we have found the resultant x component. Now for the y component. Fry equals plus or minus f1y plus or minus f2y. Now, as you recall, f1 has an extension line to the z-axis and x-axis, which means it's on the zx plane, and its y component is 0. So we can just cross it out there. FRY then equals F2's y component, which is going to be in the positive direction, and it will be F2 times an angle. Once again, we have a right triangle that can be made up of the y-axis, F2, and then a diagonal line between the two of them. That right triangle's angle is beta. So F2 can be found by, or I'm sorry, FRY can be found by the cosine of beta times F2. And our resultant y component is positive 282.843. Whenever you realize that that component and a component is 0, you can just cross it out at that point and you no longer have to deal with it. Next, we're going to find the resultant z component. So FRZ equals, well, F1's z component is in the positive z direction, and that's going to be F1 times, notice we've got 3 corresponds to the z-axis, 5 corresponds to F1. 3 over 5 times F1. F2 is going down below the xy plane. It has a negative z component. Now we can take F2 and multiply it by the cosine of gamma, because gamma is the angle between F2 and the z-axis. Once again, we can make a right triangle between the z-axis, F2, and then a diagonal line between the two. There would be a right angle there, and this angle up here would be 60 degrees, gamma. Now we can plug all our numbers in, and the resultant z component, FRZ, is a positive 160. The next step here is to draw another working diagram. In this case, I have drawn all 3 of my resultant forces on their respective axes, FRX on the x-axis, FRY on the y-axis, and FRZ on the z-axis. Notice that I don't have a sign convention here. We've already established what positive z, x, and y are for this particular problem, so you don't need to re-establish that. I'm going to go ahead and draw a box using these 3 forces to help illustrate what the result is going to be. I find it easiest to start by extending the lines that represent FRZ. So in this case, I will start at FRY and draw a line straight up. The same thing at FRX. We can also draw FRY out this way and FRX out this way. Notice that the angles at which I'm drawing these forces correspond to the axes. There's my cube, or my box. You can see that the resultant force is going to come above the XY plane. I'm going to clean this up for sake of this example. Now I'm going to draw the resultant force. The resultant force starts at the origin and extends up to the opposite corner of the box. Now I also want to include some angles here for each of these, because when I report FR, I can't just give a magnitude. I also need to give its coordinate direction according to the instructions on the problem. In order to define its coordinate direction, I will need to provide an angle off of each axis. So the angle off of the x-axis is right here, and I will refer to that as delta. The angle off of the y-axis is right here, and I will refer to that as epsilon. And the angle off the z-axis would be measured from FR up here. And I will refer to that as phi. So now I can find FR. And FR, when you have a box such as this, sort of the three-dimensional version of Pythagorean's theorem, FRX squared plus FRY squared plus FRZ squared. Plugging the values in, we find that FR equals 753.658 pounds. And notice that there is no sign on that resultant force, and that's because we haven't determined the angles for it yet. It would be incorrect to write positive or negative on that. That's strictly a magnitude. Now when we look at this problem, we will see that we have, once again, three triangles. I'm going to start solving for delta. If we were to draw a right triangle, we could draw a right triangle between the x-axis, FRX, FR, and then a diagonal line between the two. So that would be my right triangle right there, and its angle is delta. So solving that right triangle, we could say that the cosine of delta equals adjacent over hypotenuse. So that would be FRX over FR, which means that delta equals the inverse cosine of FRX over FR. Plugging the values in, delta equals 25.542 degrees. Next, I'm going to solve for epsilon. Epsilon equals the inverse cosine of adjacent over hypotenuse, FRY over FR. Epsilon then equals 67.9575 degrees. And finally, we can solve for phi in exactly the same way. Phi equals the inverse cosine of the adjacent side, which for phi would be FRZ, over the hypotenuse, which is FR. So phi equals 77.7430 degrees. FR equals 753.7 pounds. Delta equals 25.54 degrees. Epsilon equals 67.96 degrees. And phi equals 77.74 degrees. So that is how you report an angle in coordinate format. Once again, coordinate means that the angles share the same ordinate or the same origin. So all of these angles are measured off of each of their respective axes.